Now we want to try another example of finding arc length, but this time the integral might not be so easy to find by hand. So we'll notice that g of x is given right here, which is negative x squared plus 9. And we want to find the arc length over the interval 0, which is less than or equal to x, which is less than or equal to 3, which conveniently enough is what I already drew for my graph. So that works out nicely for me. All right, so we need the derivative, which is g prime of x, which is very simply negative 2x. And then the arc length, little s, is equal to the integral from 0 to 3 square root 1 plus, and then we want negative 2x squared dx, which is the integral from 0 to 3 of the square root of 1 plus 4x squared dx. Now you'll notice this is not actually an integral that is possible to find by hand at this point, knowing what we know with our basic integral sheet and u substitution. So it's not possible with u substitution and our small integral reference sheet. There will be other ways we can do this. In chapter 8. That's going to be a fun chapter. All right, so that means that we're just going to use Desmos. So let's go to Desmos. And we're looking for, let's see which integral. This is example 2, so right here. So the arc length would be right there. And the beautiful thing about Desmos, of course, I don't even have to technically find the derivative in Desmos. I can just type f prime of x, square it, and say I want it from 0 to 3, and it knows what I'm doing. So it's 9.747. And it would be feet because we're told at the top that x and y are in feet. Which leads us to, we are going to have to use technology and estimation for a lot of these. Even though it's a pretty straightforward integral, it turns out to be something really tough to find. That has a lot. So we will use Desmos to find decimal approximations. A lot in this section, and actually the next section as well. Both of these two sections on arc length and surface area require a lot of just technology approximations. Now I say that, but the next example doesn't. The next example can be done by hand, although it's going to be a little bit tough. All right, so we want to verify that the distance shown here in this arc is which is 1/8 of the circle, is 1/8 of the circle's circumference. So that's what we want to verify. I mean, we kind of know it logically, but we want to prove it. All right, so first of all, let's talk about circumference. The circumference of a circle is the distance around the circle. So circumference is 2 pi r. That's the formula for it. Now, if we look at our particular circle, our circle has a radius of a, so it would be 2 pi a. So 1/8 of the circumference would be 1/8 times 2 pi a, which would be pi a over 4. All right, so we want to keep that in mind for later reference because that's what we're trying to argue, that it's equal to 1/8 of the circumference. That's what 1/8 of the circumference is. So now we're going to see if we can prove it with the arc length formula that this actually works. Sneaky, huh? All right, so we start off with the arc length formula, which is s is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. Now, one of the tricky bits is that we need to find what f prime of x is. So you'll notice that you're given f of x, you're given the value of the function. It's right up here, right? This is f of x. So we need to find f prime of x. And notice, by the way, f of x is equal to, actually, sorry, I'm having pen problems. I'm going to call this equal to f of x, just right there. That is also equal to a squared minus x squared to the 1/2. All right, now I need to go find the derivative somewhere because I'm going to need it, so I'm just going to do it right down here. The derivative of that would be, well, we bring the 1/2 down, then it's a squared minus x squared to the negative 1/2 times the derivative of the inside. Now remember, a is a constant, so that doesn't enter into it. It's the derivative of the negative x squared, which would be negative 2x, thanks to chain rule. All right, well, that is equal to, the 2's will divide away, because 2 divided by 2 is 1. So it leaves you negative x over the square root of a squared minus x squared. So just kind of keep that piece in mind as well, because we're going to need it on our lovely, lovely derivative function right here. All right, so then we want the integral from, well, something to something. We'll figure that out in just a second. But I do know that it's the square root of 1 plus, and then this is my derivative. So I'm going to take that derivative, I'm going to square it. So that'd be negative x over the square root of a squared minus x squared. Now what about my x values? I start over at the left and I work my way to the right. So if I look at my arc on my circle, the x value here, which is the start, is x equals 0. So we're at 0 here. And we move our way over here to the right, which is x equals a square root of 2. So this is the end. A over the square root of 2. All right, so that means that those are my limits of integration. I'm going to go from 0 to a divided by the square root of 2. All right, well, a couple things. One, I noticed that when I square a square root, that's going to disappear. So this is equal to the integral from 0 to a divided by the square root of 2. And then it's the square root of 1 plus, well, negative x when we square it is x squared over a squared minus x squared dx. Now, I want to combine like terms because I'm going to try to do this by hand. So I want to change that 1 into the same denominator as my other function. So this is going to be equal to the integral from 0 to a divided by the square root of 2. I'm going to change that 1 into a squared minus x squared over a squared minus x squared. Right? That's the 1. So I'm changing it. And then I'm going to add to it x squared over a squared minus x squared dx. All right, well, when you add these up and combine like terms, that would be equal to the integral from 0 to a divided by the square root of 2. When you add these up, it'll be a squared minus x squared plus x squared, which is just the square root of a squared, divided by a squared minus x squared dx. In other words, negative x squared and a positive x squared disappear. All right, lovely. But the square root of a squared is a, so I can just pull that out. So I can make it a times the integral from 0 to a divided by the square root of 2. And I'm left with the square root of 1 divided by a squared minus x squared dx, which, if that's starting to look familiar to you, that's because it should. So that is a integral from 0 to a divided by the square root of 2. And then it's 1, because the square root of 1 is 1, over the square root of a squared minus x squared. And that is a formula we know. We actually have that formula on our derivatives and integrals sheet. Actually, it's the integral portion, obviously, since we're taking an integral here. So if I look at our sheet, looking familiar? So it's that one right there, right? Square root of a squared minus u squared. So in our case, u is x. So this is formula number 18. So this is equal to a, still out in front. Oh, actually, I'll put it in the next step because I'm actually taking the integral now. So this is a times the arc sine of x over a. And we're taking that from 0 to a divided by the square root of 2. Okay, so that would be a out in front still sitting there. And then it's the arc sine of a divided by the square root of 2 divided by a minus the arc sine of 0. All right, so a couple things. This is 0. It's 0 because you're looking for the angle that would make, right? Because the angle that has a sine, sine of 0 is 0, therefore arc sine of 0 is 0, right? This is the angle that would make, right? 0 is the angle that would make a sine value of 0. So this is done. This is 0, right? The angle 0 has a sine of 0. This over here, what happens is the a's actually cancel because a divided by a divides into 1. And so you're left with a out in front and then the arc sine of 1 over the square root of 2 because the a's disappeared. Minus 0, right? So that's irrelevant. So arc sine of 1 over the square root of 2. So you're looking for an angle that would have a sine value that's 1 over the square root of 2, which is right here at pi over 4. So at pi over 4, it's 1 over the square root of 2, 1 over the square root of 2. Those are the values for pi over 4. So this must be pi over 4. So this is a times pi over 4. That's the angle that would have 1 over the square root of 2 as its sine value. And you know what that is? That's pi a over 4, which is 1/8 of the circle. We proved it. Ooh, forgot my C in there. I was so excited that we proved it. We verified. It did in fact equal 1/8 of a circle. It is in fact, or 1/8 of the circumference of the circle. Hooray! In case you're interested, I did verify it in Desmos as well. So I have the arc length calculations right there. So I said I want to go from 0 to a divided by the square root of 2 of 1 plus f prime of x squared. And I, of course, defined f of x as the square root of a squared minus x squared. And sure enough, pi a over 4, they are one and the same. Now keep in mind, the values there are based on what I set a to be. So if I change my a, it will change what those values are. But nevertheless, you can see that they're equal to each other.